Given here two terms, 150 for Chris's first half marathon, and then 147 for his second. And we're asked to try and model it using a geometric progression. So let's try and do that. A geometric progression is basically when you have a starting term A, and then every time you're timesing by R. So the next term would be AR. And therefore, in this case, to work out R, we need to just do the second term divided by the first term. So we've got A is 150 and R is going to be 147 divided by 150. We can leave it as a fraction. Let's see what it comes out to be if we put it on a calculator. Okay, so 0.98. So it's going down by 2% every time. Right, Chris sets himself a target of completing a half marathon in less than 120 minutes. Show that this model predicts that Chris will achieve his target on his 13th half marathon. So we can now write down the nth term of the geometric sequence is actually a r to the n minus 1. Okay, because the first term has basically r to the power 0, and then it's r to the power 1 and so on. It's always 1 less than n. So in our case, it's going to be 150 times 0.98 to the n minus 1. And we're interested, okay, so his achieve his target on his 13th. So we just need to sort of check that he doesn't do it in his 12th, basically. So I'm going to find U12 first of all. I can just put this in my calculator. So 0.98 to the 11. That's going to be 120.109. Okay, so still more than 120 minutes. Whereas, yeah, you can see when we times by 0.98, that's going to be smaller, but let's just find out the value. Just times by a further 0.98, or do just put 0.98 to the 12 in, and we're going to get 117.70. I'm just going to say as required. You could write a little sentence saying, yes, this shows that Chris achieves his target after his 13th half marathon. Maybe I say that this is greater than 120, and then this is less than 120. We're then told after 12 months, Chris has spent a total of 2,974 minutes to the nearest minute running half marathons, and we have to work out how many half marathons he's run. So essentially, we're dealing with the sum of times, the sum of a geometric series, and that is given by Sn equals a 1 minus r to the n over 1 minus r. That's given in the formula book. So for us, we can replace it. We can write 2974 equals, and then our a is 150, and 1 minus our r is 0.98. Okay, and I've created an equation. It's actually an exponential equation because n is a power. So next thing to do, well, this is going to be 0.02, so I'm going to multiply that through. So 2974 times 0.02, or you can put it in as a bracket, 1 minus 0.98 if you want to be careful. So 59.48. And then I'm going to divide through by 150 as well. So that will equal 1 minus 0.98 to the n. Okay, so a bit of rearrangement. I'm going to do 1 minus the left-hand side equals the 0.98 to the n. Not 6034. Wait, was it that? Sorry, I might have made a mistake there. 6034. Sorry, to swap those two around. just going to delete it. Okay, it's now set up in the right way to be able to deal with this. So I'm going to take logs. Actually, you can either take logs to both sides, or if you remember, basically, if you ever have, say, okay, let's do an example. Log to base 10 of 100 is equal to 2, because 10 to the power 2 is 100. And actually, that's another way of writing it. So what we could instead write down is log to base b of c is equal to a. That is the same as saying that b to the power a is equal to c. So when we have something like this, actually we can then go backwards and we can say, oh, you know what? N, I mean that's the c, that's we want to work out what a is. Well, it's going to be log to base 0.98 of that 0.6034. We can just put that directly in our calculator. If you're not happy about that, then the alternative is to take log to base 0.98 of both sides. Okay, absolutely valid way of doing it. And sometimes I tell people to do this because it's a little bit easier maybe than remembering this kind of idea. But actually, this is at the heart of logs, so it is worth getting your head around. Um, so the fact is that then you can bring the n down using the third rule of logs, and then this cancels out because it's just 1, and you get exactly the same answer. You can also take log to other bases like 10, but in this case, it's just going to be easiest to use this base. So log 0.98 to the answer, and we get 24.999. So clearly, like we know, we round it to the nearest minute, it's going to be 25 marathons. In the last part, it says give 2 reasons why this model may not be appropriate when predicting the time for a half marathon. Well, first of all, as n approaches infinity, i.e., as we have more and more marathons, you could word it that way, un is actually going to approach 0. So, in other words, Chris's time will continue to improve. And it's not eventually over time, if he does enough, it would go down to like 1 minute. He'd have to do a lot of marathons to get there, but he would get there. So that's not really realistic. He's gonna sort of peak at some point and then not really improve from then on. It's not going to continue to go down by 2% every time. So that's one reason. And then another possible reason, there's more than these 2 reasons, but these are some good reasons. So the model does not incorporate other factors. Okay, all we're saying is every single time goes down by 2%, but some half marathons are longer than the others. So I said such as injuries, actually. Then I looked at the answers and I extended it and said conditions, which kind of encapsulates the length of the course, the wind, the rain, and so on. Okay, so there we have it. Nice question on geometric series.